Hey. Então, ah, falta aqui. Muito bem. Good morning. Okay, so this is the last part of the group theory. I will today I will give the results about the TMDs and phosphorine. I would discuss more the symmetries of these systems, the possibilities we have, and I will point what we have in the literature, because you see that the results are, we have a lot of results. And okay, so we already took a look at this material here. It's MOS2. This is a 2H stacking for this kind of TMD, okay? This is one of the types of TMD we can have, one of the symmetries. I will just give a glance how we proceed with this system. This system here, this TMD here, this kind of 2H symmetry, we have the identity. We have horizontal mirror, which is in the middle. I'm not sure you see here that the blue atoms are in a plane below the yellow atoms. So this system is the blue atoms, the middle plane is here, okay? So we have yellow atoms above and below, okay? So here's the, let me. We have the horizontal mirror. We have these two vertical mirrors here. We have C2 axis and the main symmetry axis, the C3. Here we have a C3 rotation here. The blue comes to blue, yellow comes to yellow, and we have also, okay, so we have the C3. We have this C2 axis perpendicular to the C3 axis, okay? So this is, and we also have these three vertical mirrors here. Okay, so this goes to the D3H group. Here's the character table for this group, okay? We see that we have the base functions here. XY is this irreducible representation here. The Z is gamma 2 minus. We have also these base functions, quadratic base functions in gamma 1 plus. And we have these base functions quadratic in gamma 3 plus. And we have also this representation here. So these are the candidates for Raman active representations. Okay, we have 3n atoms here. We have the rigid unit cell displacement for degrees of freedom. This is not a vibration mode, so we exclude 3. So we have 3n minus 3 vibrational modes. And here we have the main vibrational modes we have. This vibrational mode here This is just like a displacement of everybody in the same direction, and this is also the displacement in the same direction. So this guy here is the acoustic mode in the x or y direction, and this is the acoustic mode along the z direction. Okay, so we have these two. This is one acoustic mode, and this one here is the other acoustic mode. So one is the whole crystal going in this direction for gamma, and this is the whole crystal going horizontally here. Okay, the vibrational modes. We have the totally symmetric one out of plane. Is this one here is associated with this representation. We have this A2 prime here. Okay, this is infrared around Z, and this is A prime, which is this one here, and the A2 prime is this one here. So these are the vibrational modes for the monolayer, and of course we have the case. In the case we have two layer, we have different vibrational modes, but they just repeat. Okay, but we have to build the character table and so on, and for the bulk. Okay, this is the result for one type of TMD. We can have actually two more types of TMDs. In this work, we cover the H type, which can be, we can have actually two types of the H stacking. This is the ABA CBC stacking, what we call. So they look very much the same, but these two look very much the same, but they have some displacement here. So this is also the 2H type, but we have some displacement in relation to this one. Okay, but here comes the results. We in this work, so in this work here, okay, we present all the symmetry analysis for this TMD. So we start with this table here, okay. We have all these polytypes. We have 2HA, we have 2HB, and we have 2HC polytype, and we have the 1T polytype, and we have also this 3R polytype. So there are many types of TMDs, okay? And we do the structural analysis for bulk, odd number of layers, and even number of layers. We present the space groups for everybody, okay? We present the Vikov positions, okay? And we give some examples of compounds that can form this TMD. So the whole thing is packed in this work here. It's important to notice that some, depending on the number of layers, okay, you can have the inversion symmetry or not. For example, for odd number of layers, in this guy here, for monolayer, you don't have the inversion symmetry. For the bilayer, you have the inversion symmetry. So this is especially important for second harmonic generation. Okay, if you have inversion symmetry, you cannot have second harmonic generation. Okay, because you lose the nonlinear square susceptibility. This is the other the 1T type TMD. We already talked about this. I already showed these images. But here's the thing. As I told you, we did all the compilation for these space groups. Okay, it's in this paper here. It's hard. So here I reach my point in the presentation to just point, okay, how you take the information now. and we calculate the lattice vibration for n layers for all these TMDs, all these polytypes, the 2HA, 2HC, 1T polytype, and we have for all points in all high symmetry points in the first Brillouin zone, and also general for any n number of layers. Okay, so this is a very general result, which is also published here. And if you have any, if you need to see any symmetry aspect of this TMD crystals, you can go to this work. So this is basically the same, and we give for example, this table here is the noble vibrational mode for bulk TMDs, okay, at the gamma point for these guys here. This is for the 2H and this for 1T. So if you want to know which mode is Raman active for these guys, you can just go to these tables. If you want to know what is infrared, what is silent, and so on. There's one TMD that we missed in this work, okay, which is this 1T prime. This is like a monoclinic crystal. It's kind of confusing at the beginning. So this was measured by this collaborator here in US. At the beginning, I was very confused about this crystal, but then we realized the symmetry. This is the view, the up view from this kind of material here. This is the molybdenum telluride, and for the bulk, okay, and for odd number of layers, it has this symmetry here. We have a mirror. We have a horizontal mirror, which is basically, if you look at the monolayer, is passing through here, okay. But this is non-symmetric, and we also have C2 axis here, and we also have the inversion. For odd number of layers, we have the inversion. So, for example, one layer or 3 layers, we have inversion symmetry. For 2 layers, we don't. Okay, this was published also in this work. The whole group theory is there. So if you want to deal with this 1T prime, is not in that paper I showed. The group theory is described in this paper here. And here is a good example of second harmonic generation. If you have odd number of layers, okay, you have the inversion symmetry, you don't see any second harmonic generation signal. If you go to the even symmetry, okay, you see it's very bright. So, for example, this is like a 6 layers or 10 layers. No, this is also 6 layers, but 10 layers here. But if the parity is odd, you don't see anything. Okay. The last part is the phosphorine systems. This is kind of interesting. When we start to deal with the phosphorine, we saw that it looks like graphene, but it's kind of is a deformation of graphene. You can deal with this if you take the deformation of graphene, because you can just go and make your phosphorine system. For example, here we have 2 different pathways, okay? We can go to the left. We start from graphene. We know graphene. We know all the space group. We know the irreducible representations, okay? And what we did here in this analysis was we can make 2 types of deformations in graphene. One, we just make a isotropic strain in one direction, okay? If you just like, if you stretch the graphene in one direction, okay, or comprise. So here, but everything is still in the same plane, okay? This is the strainy graphene, not isotropic strain, but this is the isotropic strain, okay? Just in one direction, uniaxial strain. And then we lose the six-fold symmetry here, and we go to a two-fold symmetry, okay? We go down to this group here. But this is you're losing symmetry, okay? We discussed this here. If you make some strain or deformation, you lose symmetry, but it is possible to map, okay? You just go to a lower group, okay? But it still is a subgroup of the higher order group. So we can map. There's something called compatibility relations, okay, which you can map one irreducible representation to the other reducible representation. Then we can map from graphene. If you make this type of deformation, we go to this group here. Now, this is a natural way to relax this system, okay? Some of the atoms go up and some of the atoms go down. So for example, the black atoms here, they go to a plane above, and the gray atoms go to a plane below, okay? We jump from this type of material to this type of material. They have exactly the same point group symmetry, but is slightly different, the space group symmetry. And then we go to the black phosphorus. All right, so if you take graphene, you comprise the graphene, and then you let this network relax in such a way that they do some deformation, like some atoms go up and some atoms go down. You go to the black phosphorus symmetry, okay? Now, if you comprise a little bit more, you get to the C2H1, which is the end of this story. So if you go to the right here, and you make something which is, imagine that you comprise graphene completely, okay? Some of the atoms go up, and some of the atoms go down in such a way that you still have the hexagons, okay? This is what happened. So if you want to keep the hexagons, okay, some of the atoms will go up and some will go down. This is the blue phosphorus. You lose the six-fold symmetry. You go to a three-fold symmetry, okay? Because now, if you rotate here, even if the atoms are the same, if you rotate here, this atom comes to here in a six-fold symmetry. This position is above the plane. So you lose it. So now you have only three-fold symmetry. This is the blue phosphorus, okay? And you can make one deformation, okay? And if you're still doing this, now you can comprise this, or you can just make a different deformation like this, okay? And you close the cycle here. Then we just by distorting the graphene lattice, okay, in some ways, we could map all the symmetries because they are subgroups of the highest symmetry, which is the graphene symmetry. So it's like if the graphene in the symmetry, how to say, in the symmetry, I forgot the word, even in Portuguese. Okay, so in the symmetry importancy, okay, the graphene is the highest, and all these guys, they go in the lower symmetry, and you can map, okay, from the graphene space group, you can map. From the compatibility relations, you can go to these systems. And this work was, here is the blue phosphorus, okay? We have this it's kind of obvious here that we have this threefold symmetry. Okay, you see the atoms here, and this is the black phosphorus. We have the twofold symmetry. Okay, and you see how in one of them, the type of deformation that you make for graphene is like if you squeeze the whole thing, and some atoms go up and down. Here is more isotropic. Okay, it's just in one direction. So this was kind of fun to see things from this perspective. And again, now I will just show you the type of results we have. We map all the reducible representations for vibrational modes for phosphorine systems. Okay, we call this like phosphorine-related groups. Okay, because you can have the phosphorine, the blue, and the blue and the black. But we can, like, if you make some strain, you can go down. And then we have the type of black phosphorus. You can have, even for black or blue phosphorus, you can have different type of stackings, AA or AB. Okay. The blue phosphorus also has the same symmetry for silicene, germanine, and stannine. And we map all the space groups and the irreducible representations. And also, for example, for black phosphorus, okay, this is for AA stacking. We have all the vibrational modes, all the modes that have Raman, are Raman active or infrared active, the acoustic modes, this for AA stacking and for AB stacking. Similar results for blue phosphorus. This is for AA stacking blue phosphorus. All the symmetry for n number of layers, okay? And for AB stacking, all the symmetry for n number of layers. We have the eigenvectors of the normal modes of vibration. And this is this is for graphene and for strainy graphene, okay? So I hope that you learn how to read these numbers and how to read these tables and how to have the what type of work and literature you have to go to understand all these symmetry, small numbers. I know this is encrypted, but I hope I delivered information how to encrypt this information. So I came to the end of the group theory part. I don't know if you have many questions, because I think this last part is kind of packed. And okay, let me. Any questions about these results? No? Because I want to use my time. So I think I was kind of I decided to be economic with the group theory today, because I think you may be tired of group theory. So I'd like to take the opportunity to show another aspect of our